This is the screencast for section 10.3, example 6, areas enclosed by polar curves. Well, in the past, we found area by using rectangles. This time, that's not going to help us. We have a rotation here, and then you can see the shaded piece looks kind of like a sector. Do you remember those from geometry? This paragraph on the bottom says, recall from geometry that the area of a sector of a circle is 1/2 r squared theta, where r is the radius and theta is the central angle measured in radians. So if we replace theta by the differential d theta, so we make them really small and we have a change in theta, a little change in rotation, we get the area differential dA equals 1/2 r squared d theta. So the little change in area as theta changes, which is exactly the quantity we need to integrate and get an area in polar coordinates. So basically we have the antiderivative of alpha to beta. Alpha is going to be your starting theta, beta is going to be your final theta, just kind of like on the x-axis when we were integrating we did a to b. And then of the little tiny sectors that we're going to add up. So this is a sum of the area of all these little sectors within the polar curve. So example 6, find the area of the region in the plane enclosed by the cardioid, r equals 2 times 1 plus cosine of theta. Well, I've got my formula, the antiderivative 0 to 2 pi, and I'm using 0 to 2 pi because I need a full rotation all the way around. I can see that I'm going to have to rotate all the way around the curve. It says even here theta equals 0 to 2 pi. Plus, if I'm dealing with cosine of theta, I know I'm not going to get through all those values until I go all the way around one period, so 0 to 2 pi. Now r is 2 times 1 plus cosine of theta, so that quantity is getting squared, and then of course your d theta at the end. Well, if I square the 2, I have 4, and then that times 1/2 is 2, so I'm going to put that on the outside of my antiderivative just because it's a coefficient. And then 1 plus cosine squared is 1 plus 2 cosine of theta plus cosine squared of theta. Well, if I want to do this by hand, I don't really know how to integrate cosine squared of theta very well, but I do have an identity. Cosine squared of theta is 1 plus cosine of 2 theta over 2, which I can integrate eventually. So now I'm going to take this 1/2 and then, distribute basically the denominator 2. So 1/2 plus 1 is 3/2, and then I still have 1/2 cosine of 2 theta. Well, if I distribute the 2 back in, that makes all those denominators go away, which is kind of nice. And then if I take this integral from 0 to 2 pi, I could easily do this by hand, but I will get 6 pi minus 0, which is 6 pi after evaluated from 0 to 2 pi. So there are 6 pi cubic units within this cardioid. The now try problem number 43 says, find the area of the region described inside the convex limacone r equals 4 plus 2 cosine of theta. So that's the type of curve we have here, type of polar curve we have here. Alright, so first the area inside is going to be the antiderivative of, now this only has cosine in it, so I need a full rotation. I need 0 to 2 pi to get the full curve. So I'm going to go 0 to 2 pi. And then I have 1/2, now r, which is going to be squared, d theta. Now after I square r, and then distribute the 1/2, I have a cosine squared that I would need to integrate again. So let's use that same identity and make that 1 plus cosine of 2 theta over 2. Now those two 2's will cancel out. So I just have the 1 plus cosine of 2 theta. I can integrate and evaluate from 0 to 2 pi. That's just 18 pi. So there are 18 pi cubic units in here. And we basically added up all the little sectors. So like that little sector, I'm not going in order, I probably should go this way. This little sector, some sectors over here, some more sectors. We added up all these teeny tiny little sectors all the way around and got 18 pi cubic units.